instruments. So Paul Robertson will tell us about the first performances on Sky of NEID. Paul.
Good afternoon. Thank you for being here. I'm fortunate to be giving this presentation on behalf of a large team of people. And I should emphasize that the folks shown on this slide are only the NEID instrument team. And when you start to factor in the science team, we're continuing to grow, and it's really great. Over 40 members of our team are currently present in person at EPRV. So if you ask me any detailed questions, I'll probably just point you to the local expert. I've got the baseball card here for the basics of NEID, and I'm going to try not to move anymore. It's on the 3.5 meter wind telescope at Kitt Peak. It has wavelength. It's a broad instrument. I don't know what's going on with the audio. And for a rule of thumb, I tell people, instead of just giving wavelengths, we go complete coverage from calcium to calcium. So that's calcium HK out until the near infrared calcium triplet. We have Q scheduling, full Q scheduling for NEID. NEID science now takes up over 60% of all time on WIN, and that's all Q scheduled. And so that's really benefiting everybody's science. If you need cadence observations of an EPRV target, this is a really great facility. There are two observing modes. There's the high resolution mode, which delivers about 115,000 resolving power. And we can do high precision RVs out to about V of 12. And then if you have a fainter target or you're trying to do non-EPRV science, then we have a high efficiency mode that delivers a resolving power of about 60,000. Another benefit for radio velocities in the HR mode is that you do have the simultaneous cal fiber, which can be fed with either laser frequency comb or a Fabry-Perot Etalon. So NEID, as I'll show, we're actually really happy with how NEID is doing, but it has not been without some difficult encroachments from the outside world. So we began development on the hardware in April 2016 and delivered the instrument to the observatory in October 2019. We started commissioning immediately thereafter. And just as we were sort of wrapping commissioning, the observatory was shut down due to the COVID pandemic. And so we were shut down for many months. And during that time, we actually made some hardware changes to the instrument. And so between the physical changes and the extended shutdown, when we came back online in November 2020, we essentially recommissioned the entire instrument. So 2 consecutive winters of 12-hour nights was a lot of work. So in 2021, we did pass operational readiness review and science observations began in earnest. So that lasted for about a year. And then in June of this past year, the Contreras fire approached the observatory and it was shut down. And I should just mention that there were heroic efforts on the part not just of the observatory personnel, but the firefighter crews on the mountain. You can see in this image, I don't know if I have a laser pointer here, but you can see in this image just how close all that brown stuff is, how close the fire got to the observatory. So we're very thankful to still have an observatory at all. We were finally able to restart, and by restart I mean turn on the vacuum pumps in October of last year. And then in late November, we were actually able to resume science. So I'll be showing some data that are sort of cross that gap across the fire, and I'll try to point out where that happens. See Sarah Logston's poster for more details on the fire and the recovery. NEID has excellent thermomechanical stability, so we don't use Invar or Zero-Dur for our bench. We just use aluminum, and so the trade-off is we have to invest a lot in the thermomechanical stability. And we do that through a layered system of active and passive thermal controls. We maintain vacuum using liquid nitrogen cooled active charcoal, and that liquid provides cooling that facilitates the thermal control as well. And so I'm giving here a schematic both of the instrument encased in the vacuum chamber and the active thermal system, as well as the spectrometer room that includes high quality HVAC and passive thermal enclosures. So we're really happy with how that's going. I'm showing this plot. This is showing the temperature of the instrument since the restart in October. And you can see we're still in the long exponential tail of approaching our final temperature. So I want to just point this out. This is when you're trying to maintain these levels of thermal control, it's a many months long process. And I guess the takeaway from this is try not to set your observatory on fire any more frequently than you have to. And so you can see we've been drifting down for many months now, but currently the stability is very good. So we have sort of a bulk drift that's now down below about 2 millikelvin per week. And that tracks really well with the calibration system, so we can deal with that. And then the short-term scatter, that's not a typo. We maintain temperature to about 70 microkelvin. I'm very happy about that. So it's great. I can show you thermal plots, and we have heard some talks earlier that emphasize how important that is, but I'm fortunate I can sort of show you what that translates to in terms of on-sky stability. So I'll show you results from 2 sets of targets. Is our STAR program, and I really want to emphasize this. This is something that we do, the observatory invests the time in this, and we have these 9 targets that we try to get. These are stable stars from the high-res and HARP surveys. We try to get a broad range, not just of RA values, but DEC values, so that we can compare with observatories all over the world. These data, we try to observe 2 to 3 of them every night. Those data go public immediately. So if you're trying to compare your instrument performance, we encourage you to observe these stars yourself and go and grab the NEID data. And a lot of these targets are familiar already to many of you. The other stars I'll show are from the NEID Earth Twin Survey, or NETS. This is our guaranteed time program where we're surveying a set of bright nearby targets for low terrestrial mass planets. And the target selection, the target list is public. The selection function is described in Arvind Gupta's paper, so I won't spend a whole lot of time describing that. What I'll do instead is show the RVs, or at least the RV results. So this is just showing the RMS stability of the 2 sets of stars. So we have the standard stars and then 36 of the NETS targets, where I've removed the overlap objects that are also in the standard star program. I'll also mention there are, in the standard star plot, there's 1 known planet system that's off the chart, and also 2 known giant planets from the NET survey that I'm not showing, just because I didn't want to model any planets here. So a couple of really interesting takeaways. One is that we are hitting some fairly good stability numbers. I'm also relieved to see, we're picking for our standard stars objects that had hit the high-res noise floor at 1 meter or 2 per second. And so we didn't really know if those would be stable enough for our purposes, and maybe we still really don't. But the fact that those stars are more stable than the larger NETS sample is showing that we didn't do too bad of a job of selecting standard stars. I can show also a little bit of individual measurement precision. These are just the error bars, or median error bars, on all of those targets. This is the superset of the standard stars and the NET stars. And this is color coded. This is coded by V magnitude and effective temperature. A couple of caveats here, mainly that this is using the standard CCF pipeline that all of the RVs that show up through the automated NEID pipeline get treated with. And so in particular, for the cooler stars that show those higher error bars, the line lists may not be their final versions where we're going to get the very best precision out of these targets. So something like template matching might actually yield better precision in these examples. I'll show a couple of flat lines for the individual cases. I've sort of shown you the bulk statistics. But we saw earlier HT3651. So I'm showing here our beads on a wire and our stability here over about 800 days when we bin individual nights. We're looking at something like 60 centimeters per second. Oh, I'll also mention the caveat here. We have had to do a 0-point offset before and after the fire. So those are represented, if you can see them, as circles and squares. I will also mention, as we're talking warts and all, none of the published orbital solutions to this planet are sufficient to model the NEID RVs and the public express RVs. So I have had to do a custom model to get to this number. If we take a step back, then I can show without modeling any planets, we have the same approximate 800-day baseline on Tau Ceti, and without doing any kind of modeling, we are at around 85 centimeters per second. I'll highlight a few bits of science in the time I have left. I want to mention also the combination of NEID's broad bandpass and excellent Q cadence observations allows us to open the toolbox for stellar activity characterization. I'm showing here the fascinating example of HD 26965, which has a really pronounced stellar rotation signal in the RVs and the activity indicators. This is showing H alpha from both NEID and Express was kind enough to share some of their data with us. And what we're seeing is that there's a lag between the radial velocities and the activity indicators, and that's something we're able to pick out really cleanly with these high fidelity atomic lines and that high observational cadence. So I'll point you to the splinter session that Jacob is co-organizing for more details on this and other interesting case study stars. I'll also really quickly show we are starting to see NEID science papers come out. So some of those early results are obviously Rosser-McLaughlin measurements that don't require long baselines, but we do see the benefit of Q scheduling and great precision. And we're also seeing some really neat results from TESS exoplanet characterization. So I'm out of time. I'll throw up my summary slides and take questions. Thank you.
Thank you very much, Paul. Questions? I have one meanwhile, maybe. You say that you do have a laser frequency comb. How will you operate it? Is it going to be simultaneous with the observation? Is it going to be just for calibration?
It can be. Because we're trying to maintain the lifetime of the consumables, our sort of standard operating mode is to use the laser for calibration and then use the Fabry-Perot Etalon for simultaneous cals and bootstrap that together.
Other questions? If not, we thank Paul again. Thank you very much.